My name is Peiko Wang, and I'm a PhD student from Beihang University. Today, I'm very glad to present our work entitled Multimodal Contrastive Learning for Cybersickness Recognition using Brain Connectivity Graph Representation. This work is together with Ming Li from Tsinghua University, Ziteng Wang from Beihang University, Yongjin Liu from Tsinghua University, and Lili Wang from Beihang University. Cybersickness is a major barrier to both immersion and safety in virtual reality. It's difficult to recognize because it shows strong individual differences, and complex causes. That's why effective recognize cybersickness is both important and very challenging. The motivation of our work is to recognize cybersickness more accurately by leveraging multimodal data. Single modality methods are too limited to capture the full picture, while most existing multi-modality methods rely on simple feature concatenation without modeling the intrinsic of across modalities. This gap motivates us to build a new method that explicitly captures and fuses cross-modal connectivity. In our work, we introduce a multimodal contrastive learning method for cybersickness recognition. To support and validate our method, we also build a new multimodal dataset, which includes synchronized EEG, video, and motion data collected in VR environments. Our method is centered around the brain connectivity graph representations, or BCGR. This is a task-oriented brain connectivity representation whose topology is same as the spatial layout of brain regions. The construction of BCGR is driven by the multiple strategies, including neural networks or matrix representation. It comes three variants. The first, EBCGR. EBCGR is built from EEG signals. It captures functional connectivity patterns in the brain that are directly related to the cybersickness. Because EEG provides a real-time neural responses, this representation reflects how the brain dynamically reacts during the VR exposure. An SBCGR is obtained through a standardized decomposition algorithm. Its role is to filter out individual differences and extract the consistent and task-related connectivity patterns across participants. In this way, it serves as a stable reference that strengthens reliability of multimodal fusion. An MVBCGR is derived from video and motion data. By mapping this external stimuli into the brain connectivity topology, it provides complementary information about visual and motor related processing. The three variants allow us to capture both internal neural responses and external summary inputs in a unified representation space. By representing the iteratable features of multimodal data as BCGR, we can more accurately capture the brain dynamic and that closely relate to the cybersickness. Our method includes 4 steps. First, we constructed the eBCGR from EEG data by training gender-specific graph neural networks. We choose a gender-specific design because prior studies have shown that cybersickness is strongly influenced by gender. By separating male and female participants, we reduce variability within each group and obtain the more consistent connectivity patterns. This makes the learned eBCGR more stable and also provide a solid foundation for building a unified representation later. Next, we use our proposed standardized decomposition algorithm, or SDA, to normalize the SBCGRs from different genders. The purpose of SDA is to extract common task-related connectivity patterns while filtering out individual-specific noise. The resulting SBCGR therefore serves as a robust, standardized reference that governs the multimodal fusion process. Then we design a neural prior attention encoder, or NPAE. This module maps visual and motion features into the BCGR topology and enhances specific brain regions according the prior knowledge. For example, motion data applies attention enhancement to all corresponding central regions in the BCGR. Finally, the eBCGR and MVBCGR are fused in a shared latent space through the connectivity-constrained contrastive fusion module, or CCCF. In this process, the SBCGR serves as a structural constraint to enhance multimodal connectivity and improve the quality of the learned representation. Our visualization of results show the gender-specific eBCGRs together with the SBCGR generated by SDA and their differences. The results indicate that our proposed SDA effectively filters the individual-specific features and extracts consistent connectivity patterns related to cybersickness. Connections less relevant to cybersickness, such as those in the front lobe, are excluded, while connections in the sensorimotor and vision regions are perceived. The visualization of adjacency matrix of MVBCGR before and after applying NPAE clearly show the effect. NPAE significantly enhances and amplifies the meaningful connection patterns, especially in regions related to motor and vision processing. The visualization of the future distributions before and after applying our CCCF module show the clear improvement. With CCCF, the feature changed from having mixed positive and negative samples with blurred boundaries to being well separated with much clearer boundaries. We compare our method with different modality contributions. The classification quality results shown that using all three modalities achieve the best performance. We also conduct a evaluation on the key modules to understand their contribution. The full model clearly achieved the best results, which confirm that each component plays an essential role in improving recognition. We further compare our method with the SOTA approaches. Our method achieved the highest accuracy of 84.17%, and it also reached the best specificity and AUC. Overall, the results demonstrate that our method not only outperforms the existing approaches, but also provides a more reliable solution. In this work, we propose a multimodal contrastive learning method for cybersickness recognition. Our method is built up on brain connectivity graph representation, including three variants: eBCGR, MVBCGR, and SBCGR. The CCCF modules aligns multimodal features in the shared latent space. In results, our method achieved the highest accuracy and AUC, better than several SOTA methods. However, our work still has some limitations. First, the data set only contains binary labels, so the model cannot protect the level of cybersickness. Second, we did not include extra signals like EDA due to the device limits. In the future, we plan to collect contributions, continuous label into a non-intrusive way. We will also add more physiological signals to make our method more accurate and easier to understand. Finally, we aim to test our method in more realistic VR environments. Thanks for everyone's listening.
Okay, thanks very much. So we have plenty of time for some questions if anybody has one.
Please.
Just wait for the microphone. Yeah, thanks.
Hi, thank you very much for interesting talk. I didn't pick up exactly how you collect it, if someone is cybersickness or not. So where you have a truth and
we design a pilot user study. We design a virtual environment to induce users cyber sickness. We let users play in the VR environments and then play back their videos. Let them to finish the questionnaire and tell us when they are cyber sickness.
okay. Thank you. And can I get a second question? Then do you think that this can be generalized to less props, so like less precise EEG? Would it work with I don't know how many electrodes you have, but let's say you have 20 instead of 30.
Thank you. Just for clarify, did you ask the channels of EEG device?
Yeah, exactly.
Yeah. 30 channels are used, and 2 channels are used as simple. 2 channels just for normalize the EEG data.
Yeah, but do you think if you use less, then still the method would work, or you have to use at least 32? I know it's guessing. I'm just wondering, like, if what do you think?
I think 30 channels is enough.
Is needed.
Yes,
Okay.
yeah.
Thank you very much.
Thank you.
Thank you for sharing your research. I just wonder which network measure is used in EEG.
Sorry, what?
Which network measures is used to EEG analysis?
Sorry, what is used?
I just wonder about the functional connectivity measures. There is various functional connectivity measures, some like WPRI or PEC, like that.
The BCGR topology. We use 20 system topology as BCGR topology.
No, I just wonder about the network measure.
EEG lab.
No, network measure. You give the network measure before you get in the GNN, right?
Sorry?
You have to make the edge and node.
Yeah.
Yes.
We analyze the EEG data, use EEG lab in my lab. EEG lab has a lot of algorithm to analyze the data, such as SAA, Gaussian filtering, and so on.
Okay, thank you.
Thank you.
There are other questions? We have time for one more.
Thank you very much for your nice presentation. We used to have a noise because you have a head-mounted display.
Yeah.
So noise, EEG electrode could be moved by muscle, or muscle signals could be very, not good. So how did you eliminate that kind of noise?
This is a great question. Noise in EEG is very hard to cleaning. We use a normal pipeline EEG data cleaning, just proposing ICA and by eyes. Use ICA and eyes. Is a sorry.
So I understood you just eliminated by your own decision. You by your own eyes and
yes, ICA and eyes and ICA.
Okay. The second question is human could be very different from each other. So individual difference is huge. So we have to check whether the subject is sensitive to a cyber sickness or not. Did you do that?
Yeah, everyone's EEG signal is very different. That's why we group the EEG signal by gender, because the prior study have shown that gender has very different between cyber sickness patterns is very different between genders.
My question was whether you checked their cyber sickness sensitivity. So sometimes some people are very sensitive to cyber sickness, some are not. So the signal could be very different.
We before we collect the EEG data, we excluded the very sensitive cyber sickness and very not sensitive cyber sickness to keep the data robust. Thank you.
All right, let's thank our speaker again.
Thank you very much.
Hello, everyone. My name is Brady Lee. I'm an undergraduate researcher at Northeastern University, and today I'll be sharing our work, Field Dependence as a Predictor of Cybersickness, by myself, Zachary Gatos, and Wallace S. Lagas. So very quickly, what is cybersickness? It's a form of visual-induced motion sickness, usually in VR, and remains a major barrier to everyday VR. 40 to 70% of users within 15 minutes, report symptoms within 15 minutes. It's not just a niche problem, but a break on the adoption in entertainment, training, and research. Symptoms include nausea, dizziness, and disorientation, and they can persist beyond the session. And so we want to figure out, why are some individuals more susceptible than others? Well, prior work has primarily used VR simulations like roller coasters to study cybersickness. It usually is measured with a subjective questionnaire like the simulator sickness questionnaire, and then variations of that like the VRSQ. Analysis and predictions are usually analytical models like regression, and there is an increasing popular approach of using machine learning and neural networks to predict with a lot of data, especially with biometric data like the last talk. And then there's also a lot of work with mitigations as well, like reduced field of view. But to answer this question of why people get more susceptible, we mainly turn to individual differences. Sex has shown to be a big factor, with females being more at risk. Other factors, though, include visual sensitivity, presence, prior motion sickness history, VR experience, and age, with mixed findings. Among these, though, one factor ties directly to the classical sensory mismatch theory of motion sickness, and that would be field dependence, which this paper mainly focuses on. The sensory mismatch theory is the most widely accepted theory of motion sickness. It's sought as a result of a narrow mismatch between the vestibular and the visual cues. In layman's terms, the movements seen by the eyes disagreeing with the expected signals from the organs related to balance. Field dependence is an individual difference directly linked to this mismatch theory. It's a cognitive style and continuum measuring how strongly a person's perception of objects is influenced by the surrounding visual field. So whether they rely more on their visual cues or the vestibular cues. Field-dependent individuals are those who rely more on the visual and the background, whereas field-independent individuals are those independent of the visual and the background, and so they rely more on their internal cues. We primarily measure it with the group-embedded figures test, as well as that's where the user finds a shape within a more complex shape, and then the rod and frame test, where individuals attempt to align a rod back to true vertical despite a rotation in the frame. And so field-dependent individuals would have greater error in aligning it closer to the actual rotation of the rotated frame. One of our hypotheses follows from previous work where individuals seem to adapt to become more field independent following VR immersion. Again, field independent, more weight on their internal cues. So hypothesis one, we hypothesized that higher field dependence would be correlated with greater cybersickness, and they would drop out sooner in a VR roller coaster simulation. Another hypothesis we wanted to test in this work was the measurement of field dependence. We hypothesized that in a furnished rod and frame test room with objects, the additional cues would more strongly bias the field-dependent participants away from true vertical compared to an empty run frame test room. To test our hypotheses, we recruited participants across Northeastern University. We had a user study with 50 plus participants. The final sample consisted of 45 individuals ranging from ages 18 to 32, 18 females and 27 males. We screened for normal and corrected vision and neurological conditions as well. The entire VR study was developed on Unity 3D, and we used the Vive Pro I alongside its controllers for the study. For the study design, we first had participants do an online background questionnaire, so we could keep track of sex and VR experience, as well as an asynchronous online group embedded figures test. And then during the in-person study, we first screened for corrected vision with a stereogram test. And then users completed both the empty and the furnished computerized VR rod and frame test. The next portion of the study was the VR roller coaster. Participants were told to quit the study whenever they felt too sick, and for each session, there were 3 rides. Each ride was 2 minutes long, and after each session, there would be a 1-minute break. There were at most 5 sessions, so a maximum of 30 minutes. However, many people dropped out before that, and so we measured the time to drop out, as well as the sickness questionnaire before and after each ride. So quickly, why dropout time? Well, self-questionnaires can be scale ambiguous. They vary across how people actually interpret each symptom. Time to drop out is objective. It's when an individual feels too unwell to continue, and that is a data point valuable to those designing and developing real-world VR experiences. And it reflects the combined effects of variables that push someone to stop, making it a robust target for prediction and design. For the VR rod and frame tests, we had 2 rooms, so the empty room and the furnished room. We had randomized ordering. Each room had 20 trials, and we discarded the first 5 trials to ensure individuals understood the objective and so that they got used to the controls. The error from vertical is what we're retaining here. Instead of averaging errors, we fit the errors in different room angles with a 2-term harmonic model inspired by Wallerstein's classical subjective visual vertical model. The height of the fitted wave, its amplitude, is our single field-dependent score, and it's one of our contributions on this paper, but more on that later. So here you can see our roller coaster simulation with the sickness questionnaire. It had unpredictable rotations and translations, no visible track, and no user controls. We encouraged head and eye engagement with the balloon search task, and the individual was seated in a rotating chair and continuously monitored to ensure that they felt well enough to continue. We measured the time to drop out, as well as having users complete a sickness report before and after each ride. On to some of the results. So here you can see the symptom profile. First, we were highly successful in causing dropout in a short period of time. So 82% of individuals dropped out before 17 minutes, and only 18% remained, finishing the full 30 minutes, and no emesis occurred. So here you can see the symptoms. Nausea was the most frequent and intense symptom, statistically higher than most others, and then 57.8% reported moderate to very strong general discomfort. So this figure plots dropout time against the maximum Cybersickness score reported on the questionnaire. So you can see females in orange tended to drop out sooner than males, but I want to highlight, you can notice some participants reported the same maximum sickness score, yet one might quit 5 minutes earlier than another. That's why questionnaires don't tell the entire story, and dropout time gives us an objective measure of VR tolerance that complements self-reports and captures the actual moment someone can't continue. For our harmonic fit of the rod and frame, here the thin lines are example fits from 3 individual participants. The red line is the overall fit across the sample, and the shaded band is its 95% confidence interval. The model captures the periodic bias introduced by the rotated frame, and the key metric we take away is amplitude of the wave. That's our single field-dependent score, representing how strongly someone is pulled by the visual field. This gives us a much more cleaner and more interpretable measure of visual reliance compared to traditional averages that is what we will use in our hazard model. So to tie this together, We modeled the dropout time using Cox regression. The best model combined sex and the empty room run frame test amplitude. So each unit increased in field dependence. Amplitude increased dropout hazard by 37%. And females had 126% higher hazard than males. So hypothesis 1 was supported. More field dependence meant shorter VR tolerance with our measurement. Hypothesis 2 was partially supported. The furnished room did bias people more, but its amplitude didn't predict dropout as well. That is likely because our two-term harmonic fit under-modeled the virtual cues. So field dependent matters, but sex is the stronger independent predictor here. Although one of our contributions is an open source VR roller coaster causing quick and high levels of dropout rates, we do acknowledge it is very intense. It might not be so aligned with real world VR experiences with slower sickness buildups. And then also again, the model richness, the furnished run frame test just may need richer harmonic components beyond a two-term fit. There's also some ongoing work. We're looking at eye tracking during the run frame test as an additional signal and predictor, and you can talk to me about that during the poster session tomorrow. We also acknowledge the need for larger sample sizes with any cybersickness study to allow interaction terms like sex, field dependence, presence, and other individual differences not highlighted. So our main takeaways: field dependence measured with our harmonic fit amplitude is a practical predictor of cybersickness alongside sex, which is stronger. Second, dropout time is robust, interpretable, and design relevant. Future studies should consider adopting this time to event paradigm alongside questionnaires to visualize cybersickness more fully. We also adapted Millerstein's harmonic model to VR run frame test, giving us a simple but powerful field dependent metric. And finally, we showed attempts at a seamless embedded cognitive test in natural VR environments with a furnished run frame test. This is the direction we want to head towards, a quick natural calibration that is able to predict cybersickness and employ mitigation techniques appropriately and automatically for each individual. Thank you all so much for your time. Again, my name is Brady. Please feel free to email any one of us, and I'm happy to take any questions.
Okay, thanks, Brady, for the nice talk. We have time for questions.
Hi, thank you for the nice presentation. I just had a question in regards to your dropout time measure. How did you instruct people when to drop out?
Yeah, that's a great question. So for the in-person study, we told the participant, don't push yourself too intense. We didn't want anyone throwing up, and no one did. But we tried to control to make sure that when they did drop out, it was because they were too sick. We talked to them afterwards. We ensured that no one had to leave early for anything, and if they did, we removed them from the sample. I hope that answers your question.
And maybe a follow-up question, because from personal experience, I know that even if you tell participants to not push yourself, some will stick it out for longer than others.
Yeah.
So how do you make sure that they're all at the same level of motion sickness when they drop out?
Yeah, so that's kind of part of the reason we also measured the questionnaire to kind of show alongside. But in the end, 18% of participants remained, and those mostly were because a lot of them voiced that they could just keep on going forever. Yeah, I hope that answers it.
There's a question in the back.
Thank you. I'd like to give you the same question. Did you check whether they are sensitive to previous cyber sickness or motion sickness?
Yeah, so we had a online background questionnaire before they even came in for our virtual study. So we checked like previous motion sickness history, stuff like that. For our samples and our data set, nothing really stood out.
There is no relationship between MSSQ versus...
We didn't see.
Second question is, when you cause the cyber sickness, there is several factors like rotation speed, zoom in, zoom out, and yaw and pitch and so on. So did you, what kind of factor did you use? Did you have previous studies to do your main test?
Yeah, for sure. So for this, the design of the roller coaster, we had a 21 participant kind of pilot study where we had unnatural, natural, and then combined kind of rotation and translations. And our goal for the design of that was to just make people the most sick. And so that's how we came up with the design. For the environment, we just took from an online source, open source. And again, you can read about the paper and the design, and it's open source as well. So.
Okay, my last question is, people wanted to avoid their environment to see the rotation or moving things. So their eye focus is sometimes they do trick to avoid that things.
Yeah.
Did you check with the
so
eye tracker?
I'll also just go back here just so you can see. But we had a kind of balloon search task. So to kind of keep them engaged, the balloon would pop whenever they looked at it. So we tried to keep them engaged and kind of focused on the ride, so they didn't get like.
Good. Thank you.
Thank you.
I have one question as well, since we have plenty of time. So I was intrigued by the report of different symptoms that you showed in the graph there, and that nausea was the most common.
Yeah.
Which is not surprising in the sense that it was this roller coaster stimulus, but for overall VR experiences, at least anecdotally, it seems to me that like oculomotor issues and dizziness and things like that are much more common than nausea. So nausea happens in some of these extreme environments, but not in a lot of normal kind of everyday VR experiences.
Yeah.
So I guess my question is, do you think that your study is really getting at the effects of field dependence on nausea-like symptoms specifically, or do you think it's actually getting at those effects on cybersickness in general?
Well, I think it's kind of the combined effects of when someone just feels too uncomfortable to continue. So that kind of encompasses a lot of different variables, like nausea and cybersickness as a whole. Regarding nausea, I think it's also just maybe how people interpret the questionnaire. I feel like when you ask someone things relating with motion sickness, it's usually nausea that comes up the most, not like eye strain, when answering a questionnaire.
Right. So I guess I'm asking, if you did this study in another sort of VR environment that was less nausea inducing, but maybe more eye strain inducing, do you think you'd get the same results?
I think that's definitely an interesting area to tackle because, I mean, field dependence kind of is kind of right there, right? It tackles like the visual and the vestibular mismatch, and so especially with like eye strain and stuff like that, I think that's definitely something to look into for future work.
Sure. Thank you. All right. We have more questions. Yeah. So I think we have time because we had one fewer paper. So let's go ahead and let some more questions.
I'm wondering, did you ask, maybe I missed it, how those people like or dislike a roller coaster in general? Like I get dizzy on a roller coaster in nature, so like in real world.
Yeah, in the background questionnaire, we also asked like their tolerance for just real world roller coasters. And then like after the VR study, we also just kind of had an informal chat with them.
But you put this variable into the equation or not?
No.
This would be interesting to do, I think.
Have a lot of time. So.
Hi, great job doing the presentation. How did you find your participants? Because if you say we want to make you as sick as possible, that did that not deter anybody? So what was your sampling and your participants and how did you find them?
Yeah, so we recruited across Northeastern University with flyers and like just word of mouth and like in classes, stuff like that. I think it did deter a lot of people away, right? They don't really want to throw up in a VR study. But I think we tried to advertise that it was a fun experience, it's like a VR roller coaster. We had 50 plus $50 gift card, like every 10 participants. And then, yeah, the sample was, we had a 50 plus individuals, but then the sample ended up being 45.
Based on your age, you've got young people.
Yeah.
How would you correlate for old people? Older eyes, older perception, older, all of the above.
Yeah, I think that's just something that is always a limitation in these kinds of cybersecurity studies, and that's something we definitely should be looking at more. I definitely acknowledge it's a limitation.
So essentially, you didn't recruit faculty, is what I'm getting at. You
No,
only
mostly
recruited
it was like, yeah, you can see the ages. It's mostly
young.
undergraduates and then like masters, PhDs here and there.
Old eyes
Faculty
would-
are too smart to participate in studies like that.
Well, if you do put on the form, we're gonna make you as sick as possible. That might.
For the, I mean, we did the traditional IRB. I think we really emphasized the researcher being constant. We constantly monitored the individual. So every minute of the ride, we would ask them kind of how they're feeling, and we would kind of be sure to step in and say like, "Hey, are you okay?" And they would stop. They felt comfortable enough to stop whenever they felt too uncomfortable. I think, yeah, I think we there's a bit of back and forth, but yeah, especially with the monitoring and yeah. Thank you.
All right. So if you have further questions for Brady, feel free to catch him after the
Yes.
after the
I'll also be in
session.
the poster session tomorrow as well.
Yeah.
Looking at eye gaze.
So let's thank him one more time.
Thank you all so much.
Hello everyone. I'm EM Ridwan. I'm presenting my paper beyond supervised limit. So we already know what is cyber sickness. 60 to 95% of users feel cyber sick, limiting the immersive experience. So cyber sickness is discomfort like dizziness, nausea, eye strain, similar to motion sickness. So there are a lot of measurement methods for cyber sickness, subjective based, objective based, and also like machine learning approaches. So for the subjective based approaches, there is simulation similar to sickness questionnaire, VRSQ, and fast motion sickness scale. So the FMS is the only one like measured during the simulation. And for the objective based measurement, there is physiological signals. Researcher found like correlations between cyber sickness and physiological data. So machine learning approaches basically just use the physiological data and use FMS as the labels, and there is a lot of machine learning approaches. Most of them like are supervised. So what is supervised learning? Supervised learning is a type of machine learning approach where you need the FMS, the Y level for the features like eye tracking, heart rate, and GSR, and model sees all the input and the output. But there is some limitations. So what are those? Like you need the model is like heavily dependent on level data, which is costly. You need to like spend like a lot of user study and complex and limited scalability, like frequent leveling disrupt the immersion. You are asking questions like maybe each 30 seconds or maybe each minutes, the level of sickness and all. Poor generalization, like you're using some sensors or stuff which is dependent on that particular sensor and all. Individual variability is harder to capture, like age, gender, VR experience. You have 50 participants data, those are like 18 to 32 or something like that. So what is semi-supervised learning? A technique that combines small amount of label data with a large amount of unlabeled data. So here you can see level propagation and level spreading. You have only a few level data, and it finds the similarity graph and labels the unlabeled data. And then there is self-training classifiers, like you have a classifier, you train on the label data, and in each iteration, you take the labels, pseudo labels that exceed certain threshold, and again level on those pseudo labeled and the label data, and you get pseudo levels. So here's our proposed methodology. We used 1 to 5% of label data, which we can get from user study, and 95 to 99% of unlabeled data. And we combined the label and unlabeled data and generated the pseudo levels for the unlabeled data. We use 3 different pseudo leveling techniques here: level propagation, level spreading, self-training classifier. And then we pass those pseudo levels along with the label data to the deep neural networks. For that, we use here deep TCN, CNL LSTM, and time series transformer, LSTM. Yeah, so that's the overall architecture. We use 3 different data sets: simulation 21, maze, bumpy rides. So each of these data sets, the simulation 21 has like 5 different VR simulation conditions, and the maze has like different a VR walking data set, and then the bumpy rides different terrains: flat, regular, and irregular bumps. And we used all the data, like common between the 3 data set, except for the head tracking data, because the prior studies found that it shows less emphasis, like for cybersickness. And you can see that throughout the 3 data sets, the FMS range is different. Like for the simulation 21, it's from 0 to 10, and maze it's 1 to 7, and bumpy rides is 1 to 9. So for that, we did some quantile based thresholding, as you can see in table 3. And after that, we have like all of them in low, medium, and high cybersickness. But still, you can see there is like a kind of imbalance in the data. For that, we did some class balancing with interpolation based oversampling, random 25% subsampling, and class weight adjustment. And we did some additional pre-processing with outlier removals and feature scaling. So here is our best performing our model. Here you can see it takes 5% level data and 95% unlabeled data. The self-training classifier as the pseudo leveling used as the pseudo leveler with random forest classifier. It takes the 50 samples with confidence levels greater than 0.75 and labels that as pseudo level, and it takes the label data with those pseudo levels to the deep neural network. We use our deep TCN with 3 TCN blocks and a dense layer. So here's the results. As you can see, for the 3 different pseudo leveling approaches: level propagation, level spreading, and self-training classifier with random forest, the self-training classifier showed the best performance of throughout, like from 1 to 5% of data. You can see for the 5% it is 72, 72, and 75. And in the figure 7, you can see the combined accuracy among the 3 data sets for semi-supervised and the supervised approach. In green, you can see that the semi-supervised approach with 1 to 5% of data, and throughout the 1, 2, 3, and 4 and 5 percentage of data, the semi-supervised model performed better. And here you can see that among the 3 different data set individually, For the semi-supervised and the supervised in table 8, you can see that the supervised deep TCN, and here you can see the semi-supervised deep TCN, showing that in each of the data sets, the semi-supervised approach performed better than the supervised approach. So the summary of the finding, the semi-supervised learning enables cybersickness prediction with minimal level data. The proposed framework successfully combines pseudo-leveling with deep temporal models, and self-training with deep TCN consistently outperforms the combination achieving up to 75.49% accuracy. The semi-supervised learning significantly reduces dependency on costly user studies, enhancing the model generalizability across datasets, and paves a way for scalable real-time personalized cybersickness detection in the consumer VR applications. Thank you. Any questions?
Thank you, Ridwan. So time for questions. Yes.
Next word. I have a question about your self-training. What's the output of the random forest as Cybersickness or not? Binary label?
Yeah, so the random forest with self-training, you can see like with 1% of with just 1% of label data, it's 60.12.
Yeah, only 1% label data is enough.
So it's like it's finding the similarities. Like you can see we check with the ground truth true levels, and it shows like with only 1% of level data, it's finding 60.12%. And if you think like the data we are collecting, like it's always limited. We cannot generalize for all the people in the world. Like there's always individual variability. So let's say we have 1,000 peoples of data, but still if you think in a broader scale, that can be 1%.
Thank you. Thank you.
I have a question. So in terms of the practical impact of this work, your claim is that with this semi-supervised approach that you're going to reduce the need for costly user studies. But if you still need that 90 to 95% of unlabeled data, don't you still have to collect that with a user study in the same way as you would with the supervised learning approach?
Oh, okay. That's a very good question. So the thing is, if you think like in the future we have a system that collects the, let's say, the eye tracking and the, let's say, eye tracking and all kind of physiological data, and we have them stored, but we don't have the FMS, like the feedback from the user. That's still usable in semi-supervised approach, but we cannot use that in a supervised approach, because in a supervised approach we always need the Y level. So
right, that makes sense. But are you saying that you can take that 95% of unlabeled data from any VR experience? It doesn't need to be the same VR experience as the labeled data?
So yeah, so for that reason I'm using like 3 different data sets here. Like it's collected in different conditions and different VR setups. Yeah, so
it's independent of the experience.
Yeah.
We hope.
Yeah.
Okay. Thank you. Other questions?
A very interesting result, I guess. But when we make a scale to measure human beings' feeling, it is hard to make a form reference, because your input could be a not linear thing, and we have a very different value from each other. So input is different. So we need some kind of normalization factor or some technique so that you could make some good scale. What do you think about that?
So you mean like the pre-processing and stuff, or?
Yeah, when you gather the data, and people are showing a different value, but that value is different from each other. So we need some kind of normalization factor. What do you think about that?
Yeah. I haven't think of anything like that right now, but maybe that's what I can think of.
Because I saw your dessert and showing some kind of linear or non-linear thing, and you should think about that kind of.
Yeah. So for this work, I did some, like some outliers removal and min-max normalization and stuff. And if you think like for real time when it's deployed, let's say like it's in a real environment, people are playing different games and all, we're collecting data. Yeah, maybe we need to think something in a broader scale or something like that. Yeah.
All right, if there are no more questions, let's thank our speaker and all the speakers from this session one more time.